Jupiter, the largest planet in our solar system, stands as a colossal enigma, a swirling mass of gas and storms that continues to capture the imagination of astronomers, scientists, and space enthusiasts alike. This massive gas giant, approximately 11 times the diameter of Earth, is not only a marvel in terms of its sheer size but also in its complexity and mystery. From its violent atmospheric storms to its intricate system of moons, Jupiter offers a glimpse into the dynamics of planetary formation, celestial mechanics, and the extreme conditions that can exist within our solar system. Jupiter's defining characteristic is its immense size, a feature that dominates the planet's role within our solar system. With a mass more than 300 times that of Earth, Jupiter exerts an extraordinary gravitational influence on the orbits of other planets, asteroids, and even comets. It serves as a kind of cosmic vacuum cleaner, capturing or deflecting objects that might otherwise pose a threat to planets like Earth. This gravitational force not only shapes the movement of celestial bodies but also contributes to the planet's own structure and evolution. Jupiter is primarily composed of hydrogen and helium, the two lightest and most abundant elements in the universe. This composition is similar to that of the Sun, suggesting that Jupiter might be more akin to a failed star than a traditional planet. Despite its massive size, Jupiter lacks the necessary mass to initiate the nuclear fusion processes that define stars. However, its composition and size make it a valuable object of study, as understanding Jupiter can provide clues about the processes that shape not only our solar system but also other planetary systems throughout the galaxy. The planet's atmosphere is a fascinating and turbulent place, dominated by its iconic bands of clouds that stretch across its surface. These bands are composed of ammonia crystals and other compounds that form as a result of the planet's intense atmospheric conditions. The clouds themselves are arranged in alternating light and dark bands, known as zones and belts, which run parallel to Jupiter's equator. These zones and belts are driven by powerful jet streams that blow at speeds of hundreds of kilometers per hour, creating a dynamic and constantly shifting weather system. At the heart of this weather system is Jupiter's Great Red Spot, a massive storm that has raged for at least 400 years, possibly much longer. The Great Red Spot is a giant anticyclonic storm, meaning that it rotates in the opposite direction to the planet's rotation. This storm is so large that it could easily engulf Earth, and it continues to baffle scientists due to its longevity and intensity. The mechanisms that power this storm remain elusive, but it is thought that the immense energy generated by Jupiter's rapid rotation and internal heat plays a role in sustaining it. In addition to the Great Red Spot, Jupiter's atmosphere is home to numerous other storms and vortices, many of which are smaller in scale but equally impressive in their power and complexity. These storms are driven by the planet's rapid rotation, which creates a strong Coriolis effect that causes winds to swirl and form cyclonic systems. Jupiter rotates on its axis once every 10 hours, making it the fastest rotating planet in the solar system. This rapid rotation not only shapes the planet's atmospheric dynamics but also creates a pronounced equatorial bulge, as centrifugal forces push the planet's material outward. Beneath its tumultuous atmosphere, Jupiter's internal structure remains largely hidden, though scientists have made significant progress in understanding what lies beneath the clouds. Jupiter lacks a solid surface like Earth, and its gaseous atmosphere gradually transitions into a dense fluid as pressure increases with depth. It is believed that Jupiter has a core composed of heavier elements, though the exact size and composition of this core remains subjects of debate. Some models suggest that the core could be up to 20 times the mass of Earth, while others propose that it might be much smaller or even non-existent. One of the most intriguing aspects of Jupiter's interior is the presence of metallic hydrogen, a state of hydrogen that occurs under extreme pressures and temperatures. In this state, hydrogen behaves like a metal, conducting electricity and generating magnetic fields. Jupiter's magnetic field is the strongest of any planet in the solar system, about 20,000 times stronger than Earth's. This powerful magnetic field creates a vast magnetosphere that extends millions of kilometers into space, enveloping the planet and many of its moons. The magnetosphere interacts with the solar wind, producing intense radiation belts that are similar to Earth's Van Allen belts but far more powerful. Jupiter's magnetosphere is also home to spectacular auroras, which occur when charged particles from the solar wind are funneled along magnetic field lines and collide with atoms in the planet's upper atmosphere. These auroras are similar to the northern and southern lights seen on Earth but are much more intense and can be observed in ultraviolet and infrared wavelengths. The interaction between Jupiter's magnetic field and its moons also plays a role in the planet's auroras, particularly in the case of Io, the most volcanically active body in the solar system. Io, along with three other large moons, Europa, Ganymede, and Callisto, make up the Galilean moons, named after the Italian astronomer Galileo Galilei, who first observed them in 1610. These moons are among the most fascinating objects in the solar system, each offering unique insights into planetary formation and the potential for life beyond Earth. Io, the innermost of the Galilean moons, is a world of fire and brimstone, with hundreds of active volcanoes spewing sulfur and other materials onto its surface. The intense gravitational interactions between Io and Jupiter create tidal forces that generate enormous amounts of heat, driving the moon's volcanic activity. This constant resurfacing means that Io's surface is geologically young, with few impact craters and a landscape dominated by volcanic plains, lava lakes, and towering mountains. Europa, the second moon from Jupiter, is one of the most promising candidates for the search for extraterrestrial life in our solar system. Beneath its icy crust lies a vast ocean of liquid water, kept warm by tidal heating from Jupiter's gravity. This subsurface ocean is thought to contain more water than all of Earth's oceans combined, and scientists believe that it could harbor the conditions necessary for life. The surface of Europa is crisscrossed with ridges and cracks, likely caused by the movement of ice as the ocean below shifts and flows. Recent observations have also suggested the presence of plumes of water vapor erupting from the surface, providing further evidence of the dynamic nature of this hidden ocean. Ganymede, the largest moon in the solar system, is even larger than the planet Mercury and possesses its own magnetic field, the only moon known to do so. Ganymede's surface is a mix of older, heavily cratered regions and younger, less cratered areas, indicating a complex geological history. Like Europa, Ganymede is believed to have a subsurface ocean, though it is buried beneath a much thicker layer of ice. The presence of both water and a magnetic field makes Ganymede a prime target for future exploration, as it may offer insights into the conditions that can support life. Callisto, the outermost of the Galilean moons, is a heavily cratered world with a surface that has remained largely unchanged for billions of years. Unlike the other Galilean moons, Callisto does not experience significant tidal heating, and its surface is a record of the early solar system, preserving evidence of impacts and other processes that have shaped its history. Callisto is also thought to harbor a subsurface ocean, though it lies much deeper beneath the surface than those of Europa or Ganymede. In addition to the Galilean moons, Jupiter is orbited by dozens of smaller moons, many of which are irregularly shaped and likely captured asteroids or comets. These moons form a complex and dynamic system, with interactions between them and Jupiter's powerful gravity creating a constantly shifting landscape of orbits and collisions. The study of Jupiter and its moons is not only fascinating in its own right but also holds important implications for our understanding of planetary systems beyond our own. Many of the exoplanets discovered in recent years are gas giants like Jupiter, and studying these distant worlds can provide insights into the processes that govern the formation and evolution of planetary systems. Jupiter's role as a kind of gravitational shield for the inner solar system also raises questions about the importance of giant planets in shaping the habitability of planets like Earth. Jupiter's immense gravitational influence extends far beyond its immediate surroundings, shaping the orbits of the asteroid belt and even influencing the behavior of comets that pass through the inner solar system. Some comets, known as Jupiter family comets, have orbits that are controlled by the planet's gravity, while others are captured and eventually collide with the planet or its moons. In fact, Jupiter has been observed to be struck by comets and asteroids multiple times in recent decades, providing a dramatic reminder of the planet's role as a cosmic protector. One of the most famous of these impacts occurred in 1994 when the comet Shoemaker-Levy 9 collided with Jupiter, creating a series of massive explosions in the planet's atmosphere. This event, which was observed by telescopes around the world, provided a rare opportunity to witness the dynamics of such collisions and their effects on a planetary atmosphere. The scars left by the impact were visible for months, and the event highlighted the importance of Jupiter in protecting the inner solar system from potential catastrophic impacts. The exploration of Jupiter and its moons has been a major focus of planetary science for decades, with numerous spacecraft missions providing unprecedented insights into this distant world. The Pioneer and Voyager missions of the 1970s provided the first close-up views of Jupiter and its moons, revealing the planet's complex atmospheric dynamics and the diverse geology of its satellites. These missions also discovered Jupiter's faint ring system, which is composed of dust particles ejected from its moons by micrometeorite impacts. In recent years, the Juno mission has revolutionized our understanding of Jupiter, providing detailed observations of the planet's atmosphere and interior structure. Launched in 2011 and arriving at Jupiter in 2016, Juno was designed to study the planet's composition, gravity field, magnetic field, and polar magnetosphere in greater detail than ever before. The spacecraft's unique elliptical orbit allows it to pass close to Jupiter's poles, providing unprecedented views of the planet's auroras and its swirling cloud tops. Juno's instruments have revealed a wealth of information about Jupiter's atmosphere, including the discovery that the planet's famous belts and zones extend deep into its interior. These atmospheric layers, which are visible from space as alternating bands of light and dark clouds, reach depths of thousands of kilometers, much deeper than scientists had previously thought. Juno has also detected massive cyclones at the planet's poles, some of which are as large as Earth, adding to the complexity of Jupiter's atmospheric dynamics. One of Juno's most significant discoveries concerns the nature of Jupiter's core. The spacecraft's measurements of the planet's gravity field suggest that Jupiter may not have a well-defined, solid core like Earth's. Instead, it is possible that the core is diluted, meaning that heavier elements are mixed throughout the planet's interior rather than being concentrated in a distinct central region. This finding has challenged long-held theories about the formation of gas giants and has led scientists to reconsider how Jupiter and similar planets in other star systems may have formed. Juno has also provided new insights into Jupiter's magnetic field, which is unlike any other in the solar system. The planet's magnetic field is not symmetrical, with areas of intense strength and regions of relative weakness. This asymmetry is thought to be caused by the movement of metallic hydrogen deep within the planet's interior. Understanding Jupiter's magnetic field is crucial for studying the planet's magnetosphere and its interactions with the solar wind, as well as for gaining a deeper understanding of planetary magnetism in general. The planet's magnetosphere, a vast region of space dominated by its magnetic field, is one of the largest structures in the solar system. Jupiter's magnetosphere extends far beyond the planet itself, stretching millions of kilometers into space and encompassing many of its moons. Within this magnetosphere, charged particles are trapped and accelerated, creating intense radiation belts that can be hazardous to spacecraft and instruments. These radiation belts are so powerful that they pose significant challenges to future missions, necessitating the development of special shielding to protect both equipment and, eventually, human explorers. One of the most striking features of Jupiter's magnetosphere is its interaction with its moons, particularly Io. As Io orbits within the magnetosphere, it generates a massive electrical current known as the Io flux tube, which carries millions of amperes of electricity between the Moon and Jupiter's magnetic poles. This current creates spectacular auroras at Jupiter's poles, which are far more powerful than those seen on Earth. The interaction between Io and Jupiter's magnetosphere also drives volcanic activity on the Moon, contributing to its status as the most volcanically active body in the solar system. As scientists continue to study Jupiter's magnetosphere, they are gaining new insights into the fundamental processes that shape planetary magnetic fields and their interactions with the surrounding space environment. These studies have important implications not only for our understanding of Jupiter but also for other planets in the solar system and beyond, including exoplanets orbiting distant stars. In addition to studying Jupiter itself, the exploration of its moons has become a key focus of planetary science, with several missions planned or already in progress to investigate these fascinating worlds. Europa, in particular, has drawn significant attention due to its potential to harbor life. The Europa Clipper mission, set to launch in the 2020s, will conduct detailed reconnaissance of the Moon's surface and subsurface ocean, using a suite of instruments to study its ice shell, ocean, and the chemistry of its surface. Europa's ocean is one of the most intriguing targets for the search for extraterrestrial life in the solar system. Despite being located far from the Sun, Europa's ocean is kept warm by tidal heating, which could create the conditions necessary for life to exist. Scientists believe that hydrothermal vents on the ocean floor, similar to those found on Earth, could provide energy and nutrients to support microbial life. The discovery of life on Europa, even in its simplest form, would have profound implications for our understanding of life in the universe, suggesting that life could emerge in a wide range of environments beyond Earth. Ganymede and Callisto, though less well known than Europa, are also of great interest to scientists. Ganymede's unique magnetic field and potential subsurface ocean make it an intriguing target for future exploration, while Callisto's ancient, heavily cratered surface offers a window into the early history of the solar system. Both moons could provide valuable clues about the processes that shape icy worlds and their potential to support life. As we look to the future, the exploration of Jupiter and its moons promises to continue yielding new discoveries and deepening our understanding of the solar system. Advances in technology, such as more powerful spacecraft, improved imaging systems, and sophisticated scientific instruments, will allow us to probe deeper into Jupiter's atmosphere and explore its moons in greater detail. These missions will not only enhance our knowledge of Jupiter but also inform our broader understanding of planetary science, from the formation of gas giants to the potential habitability of icy moons. In addition to robotic missions, the possibility of human exploration of Jupiter's moons has been proposed as a long-term goal. While the extreme radiation and harsh conditions of Jupiter's magnetosphere make human missions to the planet itself unlikely, its moons, particularly Europa and Ganymede, could be potential targets for future exploration. Developing the technology and expertise needed to send humans to these distant worlds would be a monumental challenge, but the scientific rewards could be immense, offering an unprecedented opportunity to study alien environments and search for signs of life. Jupiter's significance extends beyond its scientific and exploratory value. The planet has long held a prominent place in human culture, mythology, and imagination. Named after the king of the gods in Roman mythology, Jupiter has been associated with power, authority, and grandeur. In many ways, the planet lives up to its namesake, dominating the solar system with its immense size and influence. Ancient astronomers marveled at its bright appearance in the night sky, and it has been a subject of fascination ever since. The study of Jupiter and its moons also has profound implications for our understanding of our place in the universe. By studying the processes that shape Jupiter and its diverse system of moons, we gain insights into the broader dynamics of planetary formation and evolution. Jupiter's role as a guardian of the inner solar system, deflecting potentially dangerous objects, highlights the interconnectedness of celestial bodies and the delicate balance that allows planets like Earth to exist. Moreover, the search for life on Europa and other icy moons raises fundamental questions about the nature of life itself. If life can emerge in the harsh, frigid environments of these distant moons, it suggests that life may be far more common in the universe than previously thought. This possibility challenges our understanding of biology and the conditions required for life to thrive, opening up new avenues of exploration and discovery. Jupiter, with its swirling storms, powerful magnetosphere, and fascinating moons, stands as a testament to the wonders of the cosmos. It is a planet of extremes, where the forces of nature operate on a scale that is difficult to comprehend. Yet, through careful observation and exploration, we are beginning to unlock its secrets, one discovery at a time. As we continue to study this gas giant and its moons, we are not only learning about the outer reaches of our solar system but also gaining a deeper understanding of the forces that shape the universe and our place within it. The exploration of Jupiter is far from over. With each new mission, we are pushing the boundaries of our knowledge and challenging our assumptions about what is possible in the universe. From the violent storms of the Great Red Spot to the icy depths of Europa's hidden ocean, Jupiter offers an endless source of fascination and discovery. As we continue to explore this giant of the solar system, we are reminded of the boundless curiosity that drives us to seek answers to the greatest mysteries of the cosmos. As we peer deeper into the mysteries of Jupiter, we not only expand our knowledge of this magnificent planet but also enrich our understanding of the entire solar system, and by extension, the universe itself. Jupiter's unique position as a gas giant and its complex system of moons make it a microcosm of planetary and celestial phenomena, offering a laboratory of sorts for scientists to test theories about planetary formation, atmospheric dynamics, and the potential for life beyond Earth. The sheer size and mass of Jupiter contribute to its immense influence on the solar system. Its gravitational pull not only shapes the orbits of its moons but also affects the movement of comets and asteroids. Jupiter's role as a cosmic shield cannot be overstated, as it helps deflect or capture objects that might otherwise threaten planets like Earth. This protective role likely played a key part in the development and maintenance of life on our planet. The discovery of numerous asteroid impacts on Jupiter, as well as the remnants of comets like Shoemaker-Levy 9 that were absorbed by the planet, are stark reminders of the dynamic and often chaotic nature of the solar system. Yet despite its enormous influence, Jupiter remains a mystery in many ways. The more we learn, the more questions arise. One of the enduring puzzles is the precise nature of Jupiter's atmospheric processes. The planet's weather systems are not just confined to the surface. They extend deep into the planet, driven by forces we are only beginning to understand. The giant storms that rage across Jupiter's atmosphere, including the iconic Great Red Spot, seem to defy the limits of endurance and scale. Some storms have persisted for centuries, and understanding how such phenomena form and sustain themselves could reveal deeper truths about atmospheric physics. The Great Red Spot itself, a storm larger than Earth, has captivated astronomers for hundreds of years. Recent observations suggest that the storm is slowly shrinking, but it remains a powerful symbol of Jupiter's turbulent atmosphere. Scientists are particularly interested in the mechanisms that drive this massive vortex, as it offers a window into the chaotic energy that permeates the planet's atmosphere. Understanding the forces that shape the Great Red Spot could help researchers develop more accurate models of weather patterns, not only on Jupiter but also on Earth and other planets with atmospheres. Another intriguing aspect of Jupiter's atmosphere is the presence of colorful cloud bands, which are made up of ammonia, sulfur, and other compounds. These bands are divided into light zones and darker belts, creating a striped appearance across the planet's surface. The colors seen in these bands are thought to be caused by differences in temperature and chemical composition, with deeper layers of the atmosphere being hidden from view. Juno's mission has provided high-resolution images of these cloud layers, revealing intricate patterns of turbulence and vortices that further highlight the complexity of Jupiter's weather systems. Juno's discoveries have also shed light on the composition and structure of Jupiter's poles. Unlike the equatorial regions, where the cloud bands are more pronounced, the poles are characterized by swirling cyclones and less distinct banding. These polar cyclones are massive, with some spanning thousands of kilometers, and are arranged in symmetrical patterns that have left scientists puzzling over their origin. The cyclones are also incredibly stable, persisting over time despite the dynamic forces at play in the planet's atmosphere. These observations raise new questions about how such structures form and maintain their stability in an environment as chaotic as Jupiter's. As we continue to study Jupiter's atmosphere, the possibility of discovering new phenomena remains high. Jupiter's size and the extreme conditions present on the planet make it a unique laboratory for studying atmospheric processes that cannot be replicated elsewhere. The discoveries made on Jupiter are already informing our understanding of other gas giants in the solar system, such as Saturn, Uranus, and Neptune, as well as exoplanets orbiting distant stars. By comparing the atmospheres of these worlds, scientists can begin to develop a more comprehensive picture of how planets evolve and the factors that drive their atmospheric dynamics. The study of Jupiter's moons has also opened up new avenues of research, particularly in the search for life beyond Earth. Europa, Ganymede, and Callisto, with their icy surfaces and potential subsurface oceans, are prime candidates for future exploration. The prospect of finding life in these hidden oceans is tantalizing, as it would suggest that life can thrive in a wider variety of environments than previously thought. Europa, in particular, has become a focal point for astrobiologists, who believe that the Moon's ocean may contain the necessary ingredients for life, including water, heat, and organic molecules. The planned Europa Clipper mission is poised to be a game-changer in this search. Scheduled to launch in the 2020s, this mission will carry advanced instruments designed to probe Europa's ice shell and search for signs of life in the ocean below. The spacecraft will conduct multiple flybys of Europa, using radar to penetrate the ice and study its thickness, composition, and structure. By analyzing the surface features and potential plumes of water vapor that have been observed emanating from the Moon's surface, scientists hope to gather crucial data that could confirm the existence of life or at least the potential for it. The search for life on Europa has broader implications for our understanding of the conditions necessary for life to exist. If life can emerge in the dark, icy depths of a moon like Europa, it suggests that life may be far more adaptable and widespread than previously believed. This possibility has significant implications for the study of exoplanets, particularly those located in the habitable zone, around their parent stars. The discovery of life on Europa would not only expand the range of environments where life could potentially thrive but also bolster the case for the existence of life elsewhere in the galaxy. Ganymede, the largest moon in the solar system, also presents an intriguing target for exploration. With its unique magnetic field and evidence of a subsurface ocean, Ganymede could hold clues about the formation of moons and the processes that govern their evolution. The European Space Agency's JUICE, Jupiter Icy Moons Explorer, mission, set to launch in the coming years, will focus on studying Ganymede, as well as Europa and Callisto, in an effort to unlock the secrets of these icy worlds. By understanding the similarities and differences between these moons, scientists hope to develop a deeper understanding of the diversity of planetary bodies in the solar system. Callisto, often overshadowed by its more famous siblings, is a world of contrasts. Its ancient surface, heavily cratered and largely unchanged for billions of years, offers a glimpse into the early history of the solar system. Yet beneath this frozen landscape, there may be a liquid ocean, similar to those on Europa and Ganymede. Callisto's relatively undisturbed surface makes it an ideal candidate for studying the impacts that shaped the early solar system, while its potential subsurface ocean could provide further insights into the conditions that allow liquid water to persist in these distant worlds. As we continue to explore Jupiter and its moons, we are reminded of the vastness and complexity of the solar system. Each new discovery adds to the tapestry of knowledge, helping us piece together the story of how planets, moons, and stars form and evolve. The study of Jupiter, in particular, highlights the dynamic and interconnected nature of planetary systems, where the influence of one body can shape the fate of many others. Beyond the scientific discoveries, the exploration of Jupiter has captured the imagination of people around the world. From ancient mythology to modern science fiction, Jupiter has long been a symbol of power, mystery, and possibility. Its massive storms, giant moons, and captivating beauty have inspired artists, writers, and thinkers to dream about what lies beyond the familiar confines of Earth. As we continue to push the boundaries of exploration, Jupiter will undoubtedly remain a source of inspiration and wonder, a reminder of the infinite possibilities that await us in the cosmos. The journey to understand Jupiter is far from over. With each new mission, each new observation, we take another step toward unlocking the mysteries of this giant planet and its enigmatic moons. The future of Jupiter exploration holds the promise of even more groundbreaking discoveries, from the potential for life on its moons to the hidden depths of its atmosphere and magnetic field. As we continue to explore the outer reaches of the solar system, Jupiter stands as a beacon, guiding us toward a deeper understanding of the universe and our place within it. The continued exploration of Jupiter represents not only a scientific endeavor but also a philosophical quest, reflecting humanity's innate curiosity and desire to understand our place in the cosmos. As we study this colossal planet and its captivating moons, we are forced to confront fundamental questions about the nature of planetary systems, the origins of life, and the forces that govern the universe. The next phase of Jupiter exploration will likely build on the successes of current missions like Juno and the anticipated launches of Europa Clipper and JUICE. These missions are expected to expand our knowledge of Jupiter's moons, which have become focal points in the search for extraterrestrial life. The possibility that Europa, Ganymede, or Callisto could harbor life in their subsurface oceans has transformed these moons into some of the most intriguing and valuable targets for future exploration. As technology advances, the instruments we use to study these distant worlds will become more sophisticated, allowing for more detailed analyses of their atmospheres, surfaces, and interiors. Scientists hope to one day send landers or even submersibles to Europa or other icy moons, which would allow for direct sampling of the oceanic environments beneath the ice. Such missions would be challenging but could revolutionize our understanding of the potential for life beyond Earth. Even as we focus on the moons, the mysteries of Jupiter itself continue to captivate scientists. One of the most compelling areas of research involves the planet's deep interior. Juno's data have revealed that Jupiter's core may be diffuse and that heavier elements are likely mixed throughout the planet's atmosphere and mantle. This finding has significant implications for theories about the formation of gas giants. Traditionally, it was believed that Jupiter had a solid core formed from rocky material, which later accumulated vast amounts of gas to form the planet we see today. However, the idea of a more diluted core suggests that the planet's formation may have been more complex and involved a series of dynamic processes over billions of years. Studying Jupiter's formation not only helps us understand the gas giants in our own solar system, but also sheds light on the many gas giant exoplanets discovered around other stars. These exoplanets, often referred to as hot Jupiters, due to their proximity to their parent stars, differ from Jupiter in significant ways, but they may have shared similar formation processes. By unraveling Jupiter's history, scientists can refine models of how gas giants form and evolve in different environments. Additionally, Jupiter's intense magnetic field continues to be a subject of fascination. The planet's magnetosphere, which extends far beyond its moons, is the largest structure in the solar system. Understanding how this magnetosphere interacts with solar wind, cosmic radiation, and the charged particles from its moons is critical for a variety of fields, from space weather forecasting to protecting future spacecraft. The Juno mission has already revealed that Jupiter's magnetic field is far more complex and asymmetrical than previously thought, and further exploration may unlock more about the deep-seated processes that generate this field. The interactions between Jupiter's magnetosphere and its moons, particularly Io, offer another rich area of research. Io's extreme volcanic activity is driven by its interactions with Jupiter's magnetic field and tidal forces from the other Galilean moons. This creates a dynamic environment where matter is continually being exchanged between the Moon and Jupiter's magnetosphere, forming a vast plasma torus around the planet. The electrical currents generated by this interaction create auroras on Jupiter that are far more powerful than those on Earth. Beyond the immediate scientific value, these studies have practical applications as well. Understanding how Jupiter's magnetosphere operates can help scientists better prepare for the challenges of deep space exploration. The extreme radiation environments found around Jupiter present a significant obstacle to future missions, both robotic and human. By studying how radiation interacts with Jupiter's magnetic field, scientists can develop technologies and strategies to protect spacecraft and astronauts as they venture into increasingly hostile environments. The potential for human exploration of the Jovian system is a long-term goal that excites many in the scientific and space exploration communities. While sending humans to Jupiter itself is not feasible due to the planet's lack of a solid surface and its harsh conditions, the possibility of human missions to its moons, particularly Europa, is being seriously considered. Such missions would require advanced propulsion systems, radiation shielding, and life support technologies, all of which are areas of active research. While these challenges are immense, the prospect of exploring a world where life might exist beneath the ice is a powerful motivator. At the same time, the exploration of Jupiter and its moons continues to push the boundaries of what is technically possible. The spacecraft we send to the outer solar system must be able to operate in extreme conditions, far from the warmth and light of the sun. This requires innovations in power generation, propulsion, and communication. Juno, for example, is the first mission to Jupiter powered by solar energy, a remarkable achievement considering the planet's distance from the Sun. As missions venture deeper into the solar system, new technologies, such as advanced nuclear power systems or laser communication, will be essential for maintaining contact with Earth and powering scientific instruments. The desire to explore Jupiter and its moons also connects to broader questions about humanity's future in space. As we look to expand our presence beyond Earth, the outer planets represent both a challenge and an opportunity. The resources available on moons like Europa or Ganymede, including water ice and potentially other raw materials, could one day support human colonies or scientific outposts. While such ambitions are still far in the future, the exploration of Jupiter is laying the groundwork for humanity's eventual expansion into the solar system. Culturally, the exploration of Jupiter also carries deep significance. For millennia, the planet has been a symbol of power and mystery. In Roman mythology, Jupiter was the king of the gods, a fitting namesake for the largest planet in the solar system. In modern times, Jupiter continues to inspire awe and wonder. Its stunning imagery, from the swirling clouds of the Great Red Spot to the icy landscapes of its moons, has captured the imagination of artists, writers, and filmmakers. The stories we tell about Jupiter reflect our deepest desires to explore, to discover, and to understand the universe. As we move forward, the study of Jupiter will undoubtedly yield new surprises. With every mission, every new piece of data, our understanding of this giant planet deepens. But with each discovery comes new questions, reminding us that the journey of exploration is never truly complete. Whether we are probing the depths of Jupiter's atmosphere, mapping the icy surfaces of its moons, or unraveling the mysteries of its magnetic field, we are constantly reminded of the vastness of the universe and the endless possibilities that lie ahead. In the coming decades, as humanity's reach extends further into the solar system, Jupiter will remain a central focus of exploration. The data we gather will not only inform our understanding of the planet itself but will also shape our broader view of planetary science, astrobiology, and the potential for life elsewhere in the cosmos. The giant of the solar system, Jupiter stands as a reminder of the power and beauty of the universe, a symbol of the boundless curiosity that drives us to explore the unknown. Ultimately, the exploration of Jupiter is more than just a scientific endeavor, it is a testament to the human spirit. It represents our desire to push beyond the limits of what we know, to seek out new frontiers, and to ask the fundamental questions about our place in the universe. As we continue to study Jupiter and its moons, we are not only unlocking the secrets of a distant world but also embarking on a journey of discovery that will shape the future of humanity. As we continue our exploration of Jupiter, it becomes evident that the deeper we delve into the mysteries of this giant planet, the more we uncover about not only its intricate structure but also about the broader universe and our own potential for future space exploration. Jupiter serves as a cosmic frontier, a testing ground for our most advanced technologies and a harbinger of new discoveries that challenge our understanding of planetary systems and life itself. One of the most exciting developments in the exploration of Jupiter involves the potential for future manned missions to its moons. Europa, in particular, with its subsurface ocean beneath an icy crust, has sparked the imaginations of astrobiologists and space enthusiasts alike. The possibility that life could exist in the depths of this alien ocean is one of the most tantalizing ideas in modern science. While robotic missions, such as Europa Clipper, are planned to study the moon from orbit, the prospect of sending humans to Europa is a long-term goal that could open new doors in our search for extraterrestrial life. To make a human mission to Europa feasible, a host of technological challenges must be addressed. Radiation levels near Jupiter are extreme due to the planet's intense magnetic field, which traps charged particles from the solar wind and cosmic rays. Any human mission to Europa would need advanced shielding to protect astronauts from this radiation. Additionally, the icy surface of Europa poses difficulties in terms of landing and establishing a base of operations. Drilling through the kilometers-thick ice to access the liquid ocean below would require unprecedented engineering solutions. However, the potential rewards of such a mission are immense. If life exists in Europa's ocean, it could provide profound insights into the adaptability of life and the conditions necessary for its emergence. Beyond Europa, other moons of Jupiter also present intriguing possibilities for exploration. Ganymede, the largest moon in the solar system, is another prime candidate for future missions. Ganymede's unique feature is its magnetic field, the only known intrinsic magnetic field of any moon. This field is likely generated by a liquid iron or iron-nickel core, much like Earth's. Studying Ganymede's magnetic field could offer clues about the processes that generate planetary magnetospheres and their importance in protecting life from cosmic radiation. Additionally, Ganymede is thought to harbor a subsurface ocean, like Europa, although its ocean is located much deeper beneath its surface. Callisto, with its ancient, cratered surface, presents a different kind of mystery. The Moon's surface is one of the oldest and most heavily cratered in the solar system, providing a record of impacts that date back billions of years. This makes Callisto an important site for studying the history of the solar system and the frequency of collisions during its early formation. Despite its seemingly static appearance, Callisto may also hide an ocean beneath its surface, raising the question of whether all of Jupiter's large moons could potentially harbor the conditions for life. As we imagine these future missions, it's important to consider how our understanding of Jupiter and its moons has been shaped by robotic spacecraft. The Juno mission, for example, has been a pioneering effort, revealing unprecedented details about Jupiter's atmosphere, magnetic field, and internal structure. Juno's highly elliptical orbit allows it to skim close to Jupiter's poles, providing scientists with data that was previously inaccessible. Juno's observations have challenged long-standing models of how gas giants form and function. One of the key findings of the Juno mission is that Jupiter's core may be fuzzy, with heavier elements mixing into the surrounding layers rather than being concentrated in a distinct, solid core. This discovery suggests that Jupiter may have undergone a violent formation process, possibly involving collisions with other massive objects in its early history. The detailed mapping of Jupiter's magnetic field by Juno has also revealed that the field is far more complex than previously thought. Rather than being a simple dipole, the magnetic field appears to have multiple sources, with varying intensities and geometries. This suggests that the processes generating the magnetic field within Jupiter are highly dynamic and may involve interactions between different layers of the planet's interior. Understanding these processes could have broader implications for studying magnetic fields in other planets and even exoplanets. Juno has also provided breathtaking views of Jupiter's polar regions, which are unlike anything seen on the planet's more familiar equatorial regions. The poles are dominated by massive cyclones arranged in symmetrical patterns, unlike any storm systems observed on Earth or other planets. These polar cyclones are stable and appear to persist for long periods, raising questions about how they form. The exploration of Jupiter is, in many ways, a journey into the unknown, a quest that pushes the boundaries of human ingenuity, imagination, and science. As we look to the future, it is clear that Jupiter holds not only the answers to some of our deepest questions about planetary formation and the potential for life beyond Earth, but also the key to unlocking a more profound understanding of the universe itself. The mysteries of Jupiter extend far beyond its physical characteristics, its mass, its atmosphere, its magnetic field. They reach into questions that strike at the core of astrophysics, planetary science, and even philosophy. What is the nature of the processes that govern such massive gas giants? How did they form, and why do we find so many similar planets in distant star systems? What role does Jupiter play in shaping the history of the solar system, particularly in terms of how it influenced the formation of other planets, including Earth? One of the most fascinating aspects of Jupiter is the idea that its very existence has played a crucial role in the stability and development of the solar system. The immense gravity of the planet has acted as a shield, absorbing or deflecting comets and asteroids that might have otherwise collided with Earth, potentially disrupting the evolution of life. The theory that Jupiter has served as a cosmic protector of Earth has gained considerable support in recent years, as more evidence of its influence on the solar system's structure and dynamics emerges. This protective role, however, is a double-edged sword. While Jupiter has undoubtedly deflected many objects that could have caused catastrophic impacts on Earth, it has also been responsible for redirecting some objects toward the inner solar system. Understanding the complex gravitational dance between Jupiter, the asteroid belt, and the inner planets is critical for predicting future impacts and, ultimately, for safeguarding our planet. Looking to the future, missions to explore Jupiter's influence on the solar system will become increasingly important, particularly as we seek to understand the potential hazards posed by comets and asteroids. Jupiter's gravitational influence extends far beyond its immediate vicinity, and studying this influence in greater detail could provide valuable insights into the long-term stability of the solar system. Such research may also inform our strategies for planetary defense, helping to protect Earth from potential impacts. Beyond its gravitational influence, Jupiter's complex system of moons continues to be a major focus of exploration. The 4 Galilean moons, Io, Europa, Ganymede, and Callisto, are particularly intriguing, each presenting unique environments that offer opportunities to explore the boundaries of planetary science and astrobiology. Io, the most volcanically active body in the solar system, offers a glimpse into a world shaped by extreme tidal forces. The constant stretching and squeezing of Io's interior by Jupiter's gravity and the gravitational interactions with its neighboring moons generate immense heat, fueling its volcanic activity. The study of Io not only sheds light on volcanic processes but also provides a model for understanding how tidal forces can affect planetary bodies. Similar tidal forces may be at work in distant exoplanetary systems, and Io serves as a natural laboratory for studying these effects. Europa, as mentioned before, is perhaps the most promising candidate in the search for extraterrestrial life within our solar system. Beneath its icy crust lies a vast ocean of liquid water, heated by the same tidal forces that drive Io's volcanism. This ocean, hidden from view and insulated from the harsh radiation of space, may contain the necessary ingredients for life: water, energy, and the right chemical compounds. The exploration of Europa is not just about finding life. It is about understanding the conditions under which life can emerge and thrive in extreme environments. Europa may provide the ultimate test case for the idea that life can exist in places vastly different from Earth. The planned Europa Clipper mission, set to launch in the coming years, will be a major step forward in this quest. By conducting detailed surveys of Europa's surface and subsurface, the mission will gather crucial data that could answer some of the most pressing questions about the Moon's potential for habitability. If life exists on Europa, it would radically expand our understanding of the diversity of life in the universe and force us to reconsider the conditions necessary for life to evolve. Ganymede, with its magnetic field and potential subsurface ocean, offers another tantalizing possibility for exploration. As the largest moon in the solar system, Ganymede is a world unto itself, with a diverse geological history and a unique environment. Its magnetic field, the only one of its kind among moons, adds another layer of complexity to its interaction with Jupiter's magnetosphere. Studying Ganymede could provide key insights into the development of planetary magnetic fields, a process that remains poorly understood. Understanding how magnetic fields form and evolve is crucial for understanding the long-term habitability of planets, as these fields play a critical role in shielding planets from harmful cosmic radiation. Callisto, often described as the most heavily cratered object in the solar system, presents a stark contrast to the other Galilean moons. Its ancient surface has remained largely unchanged for billions of years, offering a window into the early history of the solar system. Yet beneath this frozen, battered exterior, there may be a liquid ocean, further complicating our understanding of what conditions allow for the presence of liquid water. The exploration of Callisto could provide important clues about the processes that govern the interior dynamics of icy moons, as well as their potential for harboring life. While the Galilean moons dominate the narrative, they are not the only moons of Jupiter. The planet is home to dozens of smaller moons, each with its own unique characteristics. Some of these moons, such as Amalthea, Metis, and Edristia, orbit within Jupiter's ring system, while others, like Himalaya, Lysithea, and Elara, follow more distant orbits. The study of these moons offers opportunities to explore a wide range of planetary processes, from the dynamics of ring systems to the evolution of small, irregular moons. One of the most exciting prospects for future exploration is the possibility of sending robotic landers to the surfaces of these moons. While landing on a body like Europa or Ganymede presents significant technical challenges, the potential scientific rewards are immense. A lander could directly sample the surface ice, searching for signs of organic compounds or microbial life. Such a mission would require advanced technologies, including drilling systems capable of penetrating the thick ice crusts of these moons, as well as instruments capable of analyzing the chemical composition of the ice and any material from the subsurface ocean that might be brought to the surface. The development of such technologies is already underway, with engineers and scientists working on innovative solutions to the challenges posed by these distant, icy worlds. The success of these efforts will be critical not only for the exploration of Jupiter's moons but also for future missions to other icy bodies in the outer solar system, such as Saturn's moon Enceladus or Neptune's moon Triton. As we continue to explore the Jupiter system, it is clear that each new discovery opens the door to even more questions. The more we learn, the more we realize how little we truly understand about this giant planet and its moons. Yet this is precisely what makes the exploration of Jupiter so exciting. It is a reminder that the universe is vast, complex, and full of surprises, and that our journey of discovery is far from over. In the decades to come, Jupiter will remain a focal point of exploration, not only for its scientific value but also for the inspiration it provides to humanity. As we push the boundaries of what is possible, exploring the far reaches of our solar system, Jupiter stands as a symbol of the endless possibilities that await us in the cosmos. The study of Jupiter is not just about understanding one planet, it is about understanding the fundamental processes that shape planetary systems, the conditions that allow life to emerge, and the forces that govern the universe. As we continue this journey, we are not only expanding our knowledge but also deepening our connection to the cosmos, reminding ourselves that we are part of something much larger, something awe-inspiring and infinite. In this sense, Jupiter is more than just a planet. It is a gateway to the stars, a reminder of the vastness of the universe and the boundless potential of human exploration. With each new mission, with each new discovery, we take another step toward understanding our place in the cosmos, and with it, the future of humanity, as we venture further into the unknown. The exploration of Jupiter is, in many ways, the ultimate expression of our desire to explore, to understand, and to discover the mysteries of the universe. As our journey toward understanding Jupiter continues, the scientific discoveries that lie ahead will only deepen the fascination with this colossal world. With each passing mission, we are not just gathering more data, we are unraveling the very nature of planetary systems, revising our understanding of how they form, evolve, and interact with one another. The more we learn about Jupiter, the more we realize that it is not an isolated entity, but rather a key player in the intricate ballet of celestial mechanics that defines our solar system. One area of future study that holds immense potential is the complex interaction between Jupiter and its moons. The interplay between Jupiter's immense gravitational force and the orbital dynamics of its moons, particularly the Galilean satellites, is an area that has already yielded important insights but still holds many mysteries. These moons are locked in orbital resonances that govern their movements in a delicate, synchronized rhythm. This resonance, particularly between Europa, Ganymede, and Io, exerts powerful tidal forces that shape the geologic and possibly even the biological evolution of these moons. For example, the tidal heating generated by these forces is responsible for Io's extreme volcanic activity, making it the most geologically active body in the solar system. This process also plays a significant role in maintaining liquid water beneath the icy surface of Europa, as well as contributing to the possible subsurface oceans of Ganymede and Callisto. Understanding these tidal interactions not only helps us understand the current state of Jupiter's moons but also provides insight into how moons around gas giants and other star systems might behave. This is crucial as astronomers continue to discover exoplanets and distant star systems, many of which are gas giants like Jupiter. By studying Jupiter's influence on its moons, scientists can develop models to predict the behavior of exomoons, which may be found orbiting gas giants in the habitable zones of their stars. Such moons, under the right conditions, could harbor life, just as Europa and Ganymede might. Therefore, studying Jupiter's moons offers a dual benefit. It deepens our understanding of our own solar system while also providing a framework for studying distant worlds. The study of Jupiter's magnetosphere is another rich field that promises new discoveries. Jupiter's magnetic field, the largest of any planet in the solar system, is an extraordinary feature that has far-reaching effects, not only on the planet itself but also on its moons and the surrounding space. The magnetosphere traps charged particles, creating intense radiation belts that make the space around Jupiter one of the most dangerous environments in the solar system. This environment poses significant challenges for spacecraft operating in the Jovian system, necessitating the development of advanced radiation-hardened technologies. Jupiter's magnetic field also generates stunning auroras, far more powerful than Earth's. These auroras are caused by the interaction between the planet's magnetic field and charged particles from the Sun, as well as particles ejected from Io's volcanoes. These light displays provide valuable clues about the nature of the planet's magnetic field and the processes that generate it deep within Jupiter's interior. The data gathered by the Juno mission has already revealed that Jupiter's magnetic field is far more complex than previously thought, with localized areas of intense magnetic activity. Future missions will continue to probe the depths of Jupiter's magnetosphere, uncovering more about the mysterious forces that shape it. This brings us to another major question that has emerged from the Juno mission: what lies at the heart of Jupiter? For many years, scientists believed that Jupiter, like other gas giants, had a solid core of heavy elements surrounded by layers of hydrogen and helium. However, Juno's data has suggested that Jupiter's core may be more diffuse and spread out than previously thought, possibly a mixture of rock and gas. This finding has major implications for our understanding of how gas giants form. Traditional models suggest that gas giants begin with a solid core that accumulates gas from the surrounding protoplanetary disk. If Jupiter's core is indeed diffuse, it may suggest that the planet underwent collisions with other bodies during its early formation, which could have disrupted its core and mixed the heavier elements throughout the planet. Understanding Jupiter's core is essential not only for comprehending the planet itself but also for refining our models of planetary formation. The formation of gas giants like Jupiter and Saturn played a crucial role in shaping the structure of the solar system. Their immense gravity helped to clear out the protoplanetary disk of gas and debris, and their movements may have influenced the orbits of the inner planets, including Earth. By studying the formation and evolution of Jupiter, we gain insights into the processes that shape the solar system and other planetary systems in the universe. Another exciting avenue of exploration involves the deep atmosphere of Jupiter, which remains one of the most dynamic and mysterious aspects of the planet. Jupiter's atmosphere is dominated by hydrogen and helium, but it also contains traces of other gases, such as methane, ammonia, and water vapor. The atmosphere is divided into several distinct layers, each with its own unique properties. The visible cloud tops are the result of complex chemical interactions, creating the colorful bands and storms that are visible through telescopes. One of the most famous features of Jupiter's atmosphere is, of course, the Great Red Spot, a gigantic storm that has raged for at least 350 years. The storm is larger than the entire Earth, with winds reaching speeds of up to 400 miles per hour. While scientists have made significant progress in understanding the dynamics of the Great Red Spot, questions remain about its longevity and energy source. Recent observations suggest that the storm may be slowly shrinking, raising questions about how long it will persist and what factors are driving its gradual decline. In addition to the Great Red Spot, Jupiter is home to a multitude of other storms, including smaller but still massive oval-shaped storms that dot the planet's atmosphere. These storms are the product of Jupiter's rapid rotation and the turbulent nature of its atmosphere. Jupiter's day lasts only about 10 hours, which means that the planet is spinning at an incredible speed. This rapid rotation, combined with the planet's size and atmospheric composition, creates strong jet streams that separate the planet's bands and drive the formation of storms. The deeper layers of Jupiter's atmosphere are even more mysterious. Beneath the visible cloud layers, scientists believe that the pressure and temperature increase dramatically, leading to the formation of exotic substances, such as liquid metallic hydrogen. This form of hydrogen, which behaves like a metal, is thought to exist in the depths of Jupiter and plays a crucial role in generating the planet's magnetic field. Studying these deep atmospheric layers will require innovative new techniques, as traditional spacecraft instruments are not equipped to penetrate the planet's dense clouds and high-pressure environment. The exploration of Jupiter is also a testament to the power of human curiosity and our drive to push the boundaries of what is possible. For centuries, Jupiter has captivated the human imagination, appearing in the night sky as a bright point of light and inspiring myths, legends, and scientific inquiry. From the earliest telescopic observations by Galileo to the sophisticated space missions of today, our understanding of Jupiter has grown exponentially. Yet, despite all that we have learned, there is still so much that we do not know. As we look to the future, it is clear that Jupiter will remain a central focus of planetary exploration. The upcoming Europa Clipper mission, set to launch in the 2020s, will be a major step forward in the exploration of Jupiter's moons, particularly Europa. By conducting detailed surveys of Europa's icy surface and subsurface, the mission will gather crucial data that could answer some of the most pressing questions about the moon's potential for habitability. If signs of life are detected on Europa, it would be one of the most significant discoveries in the history of science, fundamentally altering our understanding of the universe and the potential for life beyond Earth. At the same time, missions like JUICE, Jupiter Icy Moons Explorer, which is being developed by the European Space Agency, will continue to explore the broader Jovian system, including Ganymede and Callisto. These missions will provide unprecedented insights into the complex interactions between Jupiter and its moons, revealing new details about the geologic and atmospheric processes that shape these worlds. The exploration of Jupiter also has broader implications for the future of space exploration and humanity's place in the cosmos. As we push deeper into the outer solar system, we are developing the technologies and capabilities that will one day enable human missions to distant worlds. While sending humans to Jupiter itself is not feasible due to the planet's lack of a solid surface and its extreme radiation environment, the possibility of human missions to its moons, particularly Europa or Ganymede, is a tantalizing prospect. Such missions would require advanced propulsion systems, radiation shielding, and life support technologies, but the potential rewards, both scientific and inspirational, are immense. Jupiter, in many ways, represents the ultimate frontier in our solar system, a giant world that continues to challenge our understanding and expand the horizons of planetary science. With each new mission, with each new discovery, we take another step closer to unraveling the mysteries of this gas giant and its intriguing moons. Yet, even as we make progress, Jupiter reminds us of the vastness and complexity of the universe, and of how much we still have to learn. It is a symbol of the boundless curiosity that drives humanity to explore, to seek answers, and to push beyond the limits of what we know. In this sense, the exploration of Jupiter is more than just a scientific endeavor. It is a reflection of our deepest human impulses, the desire to explore, to discover, and to understand the universe and our place within it. As we continue to study Jupiter and its moons, we are not only expanding our knowledge of the solar system, but also embarking on a journey of discovery that will shape the future of humanity for generations to come. The exploration of Jupiter is a testament to the power of human ingenuity and curiosity, and it stands as a reminder of the endless possibilities that await us as we venture further into the cosmos. The future of Jupiter exploration is poised to take humanity even deeper into the mysteries of our solar system, as the ongoing advancements in technology and science continue to open new avenues for discovery. One of the most profound implications of Jupiter research is the possibility of finding extraterrestrial life, especially within the icy moons that orbit the gas giant. For decades, scientists have speculated about the potential for life in the oceans hidden beneath Europa's thick ice shell. The upcoming Europa Clipper mission, scheduled for the mid-2020s, will be a major step forward in investigating this possibility. Europa, with its smooth and fractured icy surface, is believed to harbor a vast ocean of liquid water beneath its crust, kept warm by the tidal flexing caused by Jupiter's immense gravitational pull. This internal heating mechanism may create conditions suitable for life, as we know that liquid water, warmth, and a stable environment are essential ingredients for sustaining life on Earth. Europa's potential as a habitat for life is so tantalizing that astrobiologists have ranked it among the top candidates in the search for life in our solar system. However, studying Europa is no easy task. The thick layer of ice that encases the Moon prevents direct access to the ocean below, making it difficult to determine whether life exists there. This is why the Europa Clipper mission will focus on flying through the plumes of water vapor that are believed to erupt from the Moon's surface. These plumes may offer a glimpse of the ocean's composition, potentially revealing whether it contains the necessary chemicals to support life. If the spacecraft detects organic molecules or other biosignatures in these plumes, it would be a groundbreaking discovery, providing strong evidence that life could exist beyond Earth. But Europa is not the only moon of Jupiter that holds intrigue. Ganymede, the largest moon in the solar system, is another focus of intense scientific interest. Ganymede is unique in that it possesses its own magnetic field, something no other moon in the solar system has. This magnetic field creates auroras at the poles, similar to those seen on Earth, and hints at the possibility of a subsurface ocean beneath its icy shell. The JUICE mission, Jupiter Icy Moons Explorer, set to arrive in the Jovian system in the early 2030s, will conduct detailed studies of Ganymede, as well as Europa and Callisto. The mission will focus on investigating the habitability of these moons, particularly Ganymede's potential for sustaining life. Callisto, the third of the Galilean moons to be a subject of exploration, is the most heavily cratered object in the solar system, and its surface provides a rich record of impacts stretching back billions of years. Like Ganymede, Callisto is also believed to have a subsurface ocean, although it is thought to be buried beneath a thicker layer of ice. Despite its distance from Jupiter and relative lack of geologic activity, Callisto remains a key target for astrobiological studies. Its ancient surface could contain clues about the early history of the solar system, as well as the potential for habitability in its hidden ocean. The exploration of these moons not only furthers our understanding of Jupiter's immediate neighborhood but also helps to answer fundamental questions about the potential for life elsewhere in the universe. If life can exist in the harsh environments of Europa, Ganymede, or Callisto, then it raises the possibility that life could be common throughout the galaxy, thriving in similarly extreme conditions on other planets and moons. This realization could reshape our understanding of biology and evolution, expanding the scope of where we look for life in the cosmos. As we look beyond the moons, the study of Jupiter's atmosphere and magnetosphere continues to challenge and inspire scientists. One of the key mysteries of Jupiter's atmosphere is the abundance of water. Understanding the distribution of water in Jupiter's atmosphere is crucial for piecing together the planet's formation history. It is believed that water played a significant role in the formation of gas giants, helping to bind together the gas and dust that eventually coalesced into these massive planets. However, measuring water content in Jupiter's atmosphere has proven to be difficult, as the water is mostly located deep within the planet, beyond the reach of visible light. The Juno mission, currently orbiting Jupiter, has provided invaluable data on this front. Equipped with a microwave radiometer, Juno has been able to peer beneath the cloud tops to measure the water content in different regions of the atmosphere. Early results have shown that water is not uniformly distributed across the planet, with some regions containing more water than others. These findings are helping scientists refine their models of how Jupiter and other gas giants formed, and how they accumulated the material that makes up their atmospheres. Juno's exploration of Jupiter has also shed light on the planet's intense magnetic field, which is more complex and variable than previously thought. The magnetic field is generated by the movement of liquid metallic hydrogen deep within the planet's interior, but Juno's measurements suggest that there may be additional sources of magnetism closer to the planet's surface. These findings have prompted new questions about the internal structure of Jupiter and how its magnetic field is generated and maintained over time. Moreover, Jupiter's magnetosphere, which extends millions of miles into space, interacts with the solar wind in ways that are still not fully understood. The magnetosphere traps charged particles, creating radiation belts that pose a significant hazard to spacecraft and potential future missions to the Jovian system. Understanding how these radiation belts are formed and how they behave is crucial for the design of future exploration missions, as well as for our broader understanding of planetary magnetic fields and space weather. Jupiter's exploration also extends beyond the gas giant itself to its influence on the broader solar system. The planet's immense gravity has acted as a cosmic vacuum cleaner, sweeping up asteroids and comets that might otherwise have posed a threat to the inner planets, including Earth. This role as a guardian of the solar system is one of the reasons why life has been able to evolve and thrive on Earth without constant bombardment from space debris. Studying Jupiter's gravitational influence helps us understand how planetary systems evolve and how they maintain stability over billions of years. In recent years, astronomers have discovered a growing number of exoplanets, planets orbiting other stars, many of which are gas giants similar to Jupiter. These discoveries have expanded our knowledge of planetary formation and have shown that gas giants are common throughout the universe. By studying Jupiter, we are not only learning about our own solar system but also gaining insights into the behavior of distant exoplanets and their potential for hosting life. Looking even further into the future, the continued exploration of Jupiter and its moons may one day lead to the development of new technologies that could enable human exploration of the outer solar system. While the extreme radiation and lack of a solid surface make human missions to Jupiter itself unlikely, its moons, particularly Europa and Ganymede, could be future targets for robotic and possibly even human exploration. The development of advanced spacecraft propulsion systems, radiation shielding, and life support technologies will be essential for making such missions a reality. In addition to the scientific and technological challenges, the exploration of Jupiter also raises philosophical questions about humanity's place in the universe. As we venture further into space and uncover more about the origins and nature of the planets, moons, and stars, we are forced to confront the possibility that life may exist elsewhere, and that we are not alone in the cosmos. This realization has profound implications for our understanding of life, consciousness, and the universe itself. The study of Jupiter, with its awe-inspiring storms, its dynamic moons, and its powerful magnetic field, is a reminder of the beauty and complexity of the universe. It serves as a testament to human curiosity and ingenuity, and to our ability to reach beyond the confines of our planet to explore the farthest reaches of the solar system. As we continue to send spacecraft to Jupiter and its moons, we are embarking on a journey of discovery that will not only expand our knowledge of the cosmos but also deepen our understanding of what it means to be human. The exploration of Jupiter is about more than just scientific inquiry. It is about the human spirit's unquenchable thirst for knowledge, adventure, and understanding. The gas giant, with all its mysteries and wonders, beckons us to continue exploring, to push the boundaries of what we know, and to strive for a deeper connection with the universe around us. As we continue our journey into the outer solar system, Jupiter will remain a beacon of curiosity and discovery, guiding us toward new frontiers in the exploration of space and the search for life beyond Earth. As we look to the future of space exploration, Jupiter remains a focal point of our ambitions. The gas giant holds a unique position within the solar system, both in its massive scale and its role in shaping the environment around it. Beyond its moons and atmosphere, Jupiter's immense gravitational influence has helped sculpt the paths of asteroids and comets, contributing to the dynamic nature of the solar system. This gravitational dominance not only protects the inner planets from potential impacts but also offers a natural laboratory for studying the forces that govern planetary motion and interactions. In the context of planetary science, Jupiter provides critical insights into the formation and evolution of gas giants, which are believed to be among the first planets to form in a star system. As the largest planet in our solar system, Jupiter's gravitational pull influenced the early formation of other planets and celestial bodies, helping to carve out the architecture of the system as we know it today. By studying Jupiter, scientists hope to unravel the processes that led to the creation of not only our solar system but also exoplanetary systems across the galaxy. One key area of study is the role that gas giants play in the development of potentially habitable planets. By examining the formation of Jupiter, researchers can gather clues about how gas giants influence the stability of planetary orbits and the likelihood of habitability in their star systems. In fact, many exoplanets discovered so far are gas giants similar to Jupiter, and understanding their formation is crucial for assessing the potential for life in those distant systems. The search for exoplanets has revealed a wide variety of gas giants orbiting other stars, many of which challenge our understanding of planetary formation. Some exoplanets, known as hot Jupiters, orbit incredibly close to their parent stars, in stark contrast to our own Jupiter. These discoveries raise important questions about how gas giants migrate within their star systems and how they interact with other planets during their formation. As we continue to explore Jupiter and refine our models of its formation, we gain critical information that can be applied to the study of these distant worlds. At the same time, Jupiter serves as a proving ground for new technologies and methodologies that will be vital for future exploration missions. The harsh conditions around the planet, its intense radiation, powerful magnetic field, and turbulent atmosphere, present significant challenges for spacecraft and instruments. The success of missions like Juno demonstrates our growing ability to design technology capable of withstanding such extreme environments, which will be essential as we venture further into the outer solar system and beyond. Advancements in propulsion, navigation, and robotics are opening up new possibilities for exploration, and the lessons learned from Jupiter missions will be applied to future ventures to Saturn, Uranus, Neptune, and potentially even beyond our solar system. With these advancements, we may one day be able to explore the farthest reaches of the Kuiper Belt or send probes to distant star systems, carrying with them the knowledge and experience gained from studying Jupiter. One of the most exciting possibilities for the future is the potential for manned missions to the moons of Jupiter. While the gas giant itself is inhospitable, its moons, particularly Europa, Ganymede, and Callisto, offer tantalizing possibilities for exploration and perhaps even colonization. The icy moons, with their subsurface oceans and unique environments, could one day serve as outposts for human explorers. However, such missions would require significant advancements in space travel and habitat technology to protect astronauts from the harsh conditions of the Jovian system. For now, robotic exploration remains the most feasible way to study Jupiter and its moons. The next few decades will likely see a surge in missions dedicated to unraveling the mysteries of the gas giant and its surroundings. These missions will not only deepen our understanding of Jupiter but also contribute to our broader knowledge of planetary science, astrobiology, and the evolution of the solar system. As we continue to push the boundaries of space exploration, Jupiter will remain a symbol of the challenges and rewards of venturing into the unknown. Its swirling clouds, powerful storms, and enigmatic moons are constant reminders of the complexity and beauty of the cosmos. Through continued exploration, we will uncover more about the origins of our solar system, the potential for life beyond Earth, and the forces that govern the universe. The study of Jupiter is more than just an exploration of a distant planet, it is an exploration of ourselves and our place in the universe. Each discovery made in the Jovian system brings us closer to understanding the fundamental nature of reality and our role within it. Whether we are searching for signs of life on Europa, unraveling the mysteries of Jupiter's magnetic field, or contemplating the formation of gas giants in distant star systems, we are driven by the same spirit of curiosity that has propelled humanity forward for millennia. Jupiter stands as a testament to the power of exploration and the endless potential for discovery. As we look to the stars and continue our quest to understand the cosmos, Jupiter will be a constant companion on our journey, guiding us toward new horizons and deeper insights into the nature of the universe. The exploration of Jupiter, in all its complexity and wonder, is a reminder that the universe is vast, mysterious, and full of possibilities waiting to be uncovered. As we delve further into the exploration of Jupiter and its profound mysteries, it's important to recognize the broader implications for science, technology, and humanity's understanding of the universe. One of the most compelling aspects of Jupiter is its potential to inform us about the early stages of the solar system's formation. By understanding Jupiter's composition, its core, and its role in influencing the other planets, we can piece together a more detailed picture of how the solar system evolved from a chaotic cloud of gas and dust into the orderly system we observe today. Jupiter, being the most massive planet, likely played a pivotal role in this process. It is thought that Jupiter's immense gravity influenced the migration of smaller planetesimals and may have shaped the orbits of the other planets. Some theories even suggest that without Jupiter's presence, Earth may have encountered far more frequent collisions with asteroids or comets, making the development of life less likely. This has led some scientists to consider Jupiter as a kind of cosmic protector, shielding the inner planets from potential destruction. Its gravitational field acts like a barrier, redirecting or absorbing objects that might otherwise pose a threat to Earth. In addition to this protective role, Jupiter also provides a window into the conditions of the early solar system. Because gas giants like Jupiter form early in the life of a star system, they capture material from the primordial cloud of gas and dust that gave birth to the planets. Studying Jupiter's atmosphere and composition can therefore offer clues about the makeup of the solar nebula from which the planets formed. In particular, the distribution of elements such as hydrogen, helium, and trace compounds like ammonia and methane within Jupiter's atmosphere can tell us a great deal about the conditions under which the planets coalesced. One of the major questions scientists are currently trying to answer is whether Jupiter has a solid core, and if so, what it is made of. The Juno spacecraft, which has been orbiting Jupiter since 2016, has been instrumental in studying the planet's interior through measurements of its gravitational field. Early data suggests that Jupiter may have a diffuse core composed of a mixture of rock, metal, and hydrogen that extends out to nearly half the planet's radius. This is quite different from earlier models that suggested a compact, solid core. Understanding the nature of Jupiter's core could reveal much about the process of planet formation, particularly how gas giants form and accumulate their massive atmospheres. In terms of its atmospheric dynamics, Jupiter continues to fascinate and baffle scientists. The Great Red Spot, a massive storm larger than Earth, has raged for centuries, yet its origins and long-term stability remain poorly understood. While storms on Earth are powered by the Sun's energy, Jupiter's storms are driven by internal heat sources. The planet emits more heat than it receives from the Sun, suggesting that there is significant heat left over from its formation or generated by processes deep within its interior. This heat drives powerful convection currents within the planet's atmosphere, creating the bands of clouds and intense storms that have been observed for centuries. Recent observations by the Juno mission have provided new insights into the Great Red Spot. It turns out that the storm extends far deeper into the atmosphere than previously thought, around 300 kilometers below the cloud tops. This depth suggests that the storm is driven by processes deep within the planet, rather than by surface-level winds. Additionally, Juno has discovered that the storm's shape is slowly changing over time, raising questions about how long it might continue to exist. Some models suggest that the storm could eventually dissipate, while others predict that it could persist for centuries more. Beyond the Great Red Spot, Jupiter's atmosphere is teeming with other phenomena that challenge our understanding of planetary weather systems. For example, Juno has observed massive polar cyclones, each larger than the size of the Earth, clustered around both poles. These cyclones are tightly packed together in geometric patterns and have shown remarkable stability, raising questions about how they form and why they remain so organized. The persistence and arrangement of these cyclones suggests that Jupiter's atmosphere behaves in ways very different from Earth's, governed by the planet's immense size, rapid rotation, and unique internal dynamics. As we continue to explore Jupiter's atmosphere, one of the central goals is to understand how its weather patterns compare to those of other gas giants, both in our solar system and beyond. Jupiter provides a natural laboratory for studying the dynamics of gas giant atmospheres, which can then be applied to the study of exoplanets. Many exoplanets discovered so far are gas giants, some orbiting their stars at much closer distances than Jupiter or Saturn. These so-called hot Jupiters offer a striking contrast to our own gas giants, and understanding the differences in their atmospheric behavior will help us develop a more comprehensive theory of planetary atmospheres across different environments. Another area of interest is Jupiter's magnetic field, which is by far the strongest of any planet in the solar system. Jupiter's magnetic field is about 20,000 times stronger than Earth's, and it generates a magnetosphere that extends millions of kilometers into space, far beyond the orbit of its moons. This immense magnetosphere interacts with the solar wind to create intense radiation belts, known as the Van Allen belts, which are filled with high-energy particles. These radiation belts pose a significant challenge for spacecraft operating in the vicinity of Jupiter, as they can damage instruments and electronics over time. However, the study of Jupiter's magnetic field also offers unique opportunities to learn about the planet's interior. Magnetic fields are generated by the movement of conductive materials, and in Jupiter's case, it is thought that the field arises from the movement of metallic hydrogen deep within the planet. Metallic hydrogen is a phase of hydrogen that occurs under extreme pressures, such as those found in Jupiter's core, where the hydrogen atoms are so tightly packed that they begin to behave like a metal, conducting electricity. Studying Jupiter's magnetic field can therefore provide indirect evidence about the composition and dynamics of the planet's interior. Moreover, Jupiter's magnetic field plays a key role in shaping the environments of its moons. The planet's magnetosphere traps high-energy particles that bombard the surfaces of moons like Europa, creating complex interactions between the moon's icy crust and the radiation belts. These interactions may help to explain the surface features observed on some of the moons, such as the cracks and ridges on Europa, which could be caused by the expansion and contraction of the ice in response to the varying levels of radiation. Europa, in particular, remains one of the most exciting targets in the search for extraterrestrial life, as its subsurface ocean could provide a habitat for microbial life. The radiation from Jupiter's magnetosphere could even contribute to this potential biosphere by breaking down water molecules on the surface, producing oxygen that could eventually make its way into the ocean. While the exact mechanisms for how this might occur are still being explored, the possibility of life on Europa continues to drive interest in future missions to the Moon. The Europa Clipper mission, set to launch in the mid-2020s, will conduct detailed surveys of the Moon's surface and subsurface, looking for signs of habitability and potential biosignatures. It will carry instruments capable of penetrating the ice to measure the thickness of the crust and the composition of the ocean beneath. If the mission detects chemical compounds associated with life, it could revolutionize our understanding of where and how life might exist beyond Earth. In parallel, the JUICE mission, Jupiter Icy Moons Explorer, set to launch in the 2030s, will focus on Ganymede, Europa, and Callisto, conducting detailed studies of their surfaces, subsurface oceans, and interactions with Jupiter's magnetic field. These missions represent the next great steps in our exploration of the outer solar system and could provide answers to some of the most profound questions about the potential for life elsewhere in the universe. As humanity continues its journey of discovery, Jupiter will remain a central figure in our quest to understand the cosmos. Its storms, moons, magnetic field, and immense size offer endless opportunities for exploration and learning. Each mission to Jupiter brings us closer to uncovering the secrets of our solar system's past, the nature of gas giants across the universe, and the potential for life beyond our home planet. In many ways, Jupiter represents both the challenges and the rewards of space exploration, reminding us of the vast unknowns that lie beyond the horizon and the incredible discoveries that await us. As we delve even deeper into the future of Jupiter exploration, it's important to consider the advancements in technology and our growing understanding of planetary science that will drive these missions. The next wave of explorations will not only focus on the mysteries of Jupiter itself but will also leverage our insights from previous missions to enhance our understanding of gas giants and their unique characteristics. The upcoming Europa Clipper and JUICE missions exemplify this forward-thinking approach. The Europa Clipper, with its suite of scientific instruments, is designed to conduct detailed reconnaissance of Europa's surface and its potential subsurface ocean. By employing a combination of radar, spectrometry, and imaging, the mission aims to map the ice shell's thickness, identify surface materials, and assess the Moon's habitability. Its ability to make multiple close flybys of Europa will enable scientists to gather a wealth of data in a relatively short time frame, paving the way for future missions that could land on or explore the Moon in more detail. JUICE, on the other hand, will take a broader approach by studying not only Europa but also Ganymede and Callisto. The mission's focus on Ganymede is particularly exciting, as it is the only moon in the solar system known to have its own magnetic field. Understanding the dynamics of Ganymede's magnetosphere could provide vital insights into its internal structure, including the presence of a subsurface ocean. By investigating the interactions between Ganymede's magnetic field and Jupiter's own magnetosphere, scientists hope to gain a deeper understanding of the processes that govern the evolution of celestial bodies in the harsh environment of the Jovian system. The technological innovations employed in these missions will set new standards for planetary exploration. For example, advances in autonomous navigation and data collection will allow spacecraft to operate in the complex and dynamic environments of Jupiter and its moons. The ability to collect and analyze data in real time will enable mission teams to make informed decisions on the fly, optimizing the scientific return of each mission. Additionally, improved materials and engineering techniques will ensure that spacecraft can withstand the extreme radiation levels present in Jupiter's magnetosphere, which has historically been a limiting factor for many missions. The exploration of Jupiter also raises questions about planetary protection and the ethical considerations of exploring potentially habitable worlds. As we seek to uncover the mysteries of moons like Europa, it is crucial to adhere to strict planetary protection protocols to avoid contaminating these pristine environments with Earth-based microbes. The scientific community recognizes the importance of preserving the integrity of extraterrestrial ecosystems, and future missions will need to be designed with this principle in mind. In addition to technological and ethical considerations, the study of Jupiter and its moons offers profound philosophical implications. The search for life beyond Earth has long captivated human imagination, and the prospect of discovering microbial life on Europa or Ganymede would not only be a monumental scientific breakthrough but would also fundamentally alter our understanding of life in the universe. It would challenge our notions of what it means to be alive, prompting us to reconsider our place in the cosmos and the potential for life to exist in environments vastly different from our own. Moreover, the exploration of Jupiter serves as a reminder of the interconnectedness of planetary systems. The study of gas giants like Jupiter informs our understanding of exoplanets, many of which have been discovered in the past 2 decades. As telescopes become more advanced, astronomers are now able to study the atmospheres and compositions of these distant worlds. By comparing the characteristics of gas giants like Jupiter with those of exoplanets, scientists can gain insights into the processes that govern planetary formation and evolution. The implications of this research extend beyond our own solar system. For example, understanding how gas giants like Jupiter capture and retain atmospheres can shed light on the conditions necessary for life to emerge. By studying the atmospheric dynamics of Jupiter and its storms, researchers can develop models that predict how similar processes might occur on exoplanets. This understanding could ultimately guide future searches for habitable worlds beyond our solar system. As we consider the broader picture, it's essential to recognize the role of international collaboration in space exploration. The exploration of Jupiter and its moons is not solely an endeavor of one nation or agency. It represents a collective effort by scientists, engineers, and researchers from around the world. The partnership between NASA, the European Space Agency, and other space agencies highlights the importance of pooling resources and expertise to tackle the complex challenges of exploring distant worlds. In addition to governmental collaborations, the rise of private space companies is changing the landscape of space exploration. These companies are developing new technologies and methodologies that can complement traditional space agency missions. As commercial interests in space grow, we may see innovative approaches to exploring the outer solar system, further accelerating our understanding of gas giants like Jupiter. The study of Jupiter also has implications for our understanding of climate and weather systems here on Earth. By examining the dynamics of Jupiter's atmosphere, scientists can draw parallels to terrestrial weather patterns, providing valuable insights into the processes that drive storms and atmospheric phenomena on our own planet. This cross-disciplinary research can enhance our understanding of Earth's climate, contributing to more accurate weather predictions and better preparedness for natural disasters. In light of these diverse avenues of exploration, it's clear that the journey to understand Jupiter and its moons is only just beginning. The excitement surrounding the upcoming missions to Europa and Ganymede underscores our commitment to uncovering the secrets of the solar system and, ultimately, our quest to answer one of humanity's oldest questions: are we alone in the universe? As we stand on the brink of this new era of exploration, we must also acknowledge the profound responsibility that comes with it. Each discovery brings with it the weight of ethical considerations, from planetary protection to the potential impact on our understanding of life and consciousness. As we navigate this uncharted territory, it is crucial to approach our explorations with humility and respect, recognizing that the universe is vast and full of wonders yet to be revealed. In the years to come, as we launch new missions and continue to analyze the data from previous ones, our understanding of Jupiter will evolve. We may uncover new phenomena, challenge existing theories, and make groundbreaking discoveries that will reshape our understanding of planetary science. The mysteries of Jupiter will continue to captivate scientists and the public alike, fueling a sense of wonder and curiosity about our place in the cosmos. Ultimately, the exploration of Jupiter is not just about understanding a distant planet. It is about the human spirit's desire to explore, to question, and to seek knowledge. It is a testament to our innate curiosity and our drive to push the boundaries of what is known. As we embark on this journey of discovery, we carry with us the hopes and aspirations of generations past, present, and future, an unyielding quest for understanding in a universe filled with mysteries waiting to be unraveled. As we reflect on the legacy of Jupiter exploration, we are reminded that the pursuit of knowledge is a never-ending journey. Each mission, each discovery, and each question answered opens the door to new inquiries and explorations. With each step we take into the depths of the cosmos, we are writing the next chapter in humanity's story, a story that is inextricably linked to the exploration of the stars, the search for life, and the understanding of our universe. And as we look to the future, we do so with the knowledge that the exploration of Jupiter and its moons will continue to inspire generations to come, igniting the spark of curiosity that drives us to reach for the stars. As we forge ahead in our exploration of Jupiter, we cannot overlook the profound implications that the discoveries we make will have on our understanding of planetary systems not only within our solar system but across the universe. Jupiter serves as a crucial benchmark against which we can measure and compare other gas giants and planetary systems. Its vastness, complexity, and unique characteristics provide a comprehensive model for understanding the formation, evolution, and dynamics of planets under various conditions. The insights gleaned from Jupiter's study are increasingly relevant as we identify and characterize exoplanets, worlds that exist beyond our solar system. The quest to understand the diversity of planetary types has led to the discovery of thousands of exoplanets, many of which are gas giants, some resembling Jupiter in size and others being radically different. By studying Jupiter's atmospheric dynamics, magnetic fields, and internal structure, we can develop theoretical models that help us interpret the data we gather from these distant worlds. One critical area of exoplanet research involves the study of planetary atmospheres. The methods developed to analyze Jupiter's atmosphere, including spectroscopy and imaging techniques, are now being adapted to study the atmospheres of exoplanets. By measuring the light spectra of these distant planets, scientists can infer their atmospheric composition, weather patterns, and even the potential presence of clouds, storms, or signs of habitability. Jupiter acts as a local example to refine these techniques, allowing for better interpretation of atmospheric phenomena observed in exoplanets. Moreover, the detection of exoplanets in habitable zones, regions around stars where conditions might be right for liquid water, has sparked great interest in understanding the role of gas giants in supporting life. Gas giants like Jupiter could play a significant role in stabilizing the orbits of terrestrial planets within these zones, preventing them from being subject to chaotic gravitational interactions that could lead to instability or frequent collisions. This stabilization could be crucial for the long-term development of life on smaller planets, emphasizing the importance of studying gas giants and their influence within their respective systems. As we consider the implications of our findings on gas giants, we must also reflect on the cultural and philosophical dimensions of our exploration. The search for extraterrestrial life is not solely a scientific endeavor. It intertwines with humanity's deeper existential questions about our place in the universe and the nature of life itself. The prospect of discovering life, even in microbial form, on moons like Europa or Ganymede would challenge our understanding of life's adaptability and resilience. It would force us to confront the possibility that life could thrive in environments radically different from those on Earth. The excitement surrounding the potential discovery of extraterrestrial life fuels public interest and engagement in space exploration. Educational initiatives, outreach programs, and collaborative projects encourage students and young scientists to become involved in planetary science, inspiring the next generation of explorers. As new discoveries are made, they not only expand our scientific knowledge but also invigorate our collective imagination and curiosity about the universe. In recent years, there has been a growing emphasis on interdisciplinary research that combines planetary science with fields such as astrobiology, geology, and atmospheric science. This holistic approach allows scientists to address complex questions about the origins of life, planetary evolution, and the conditions necessary for habitability. By collaborating across disciplines, researchers can create a more comprehensive understanding of how planets function and how life may arise and evolve in various environments. The collaboration extends beyond academia and government agencies to include private industry. With the rise of commercial space exploration, there is potential for innovative technologies and approaches to complement traditional scientific missions. Companies specializing in satellite technology, robotics, and advanced materials are contributing to the development of instruments that could enhance our understanding of Jupiter and its moons. The fusion of public and private efforts in space exploration signifies a new era where collective resources can be leveraged to achieve ambitious goals. As we look to the future, we should also consider the potential for in-situ exploration of Jupiter's moons. While robotic missions like Europa Clipper and JUICE are set to provide valuable data from orbit, the possibility of landing on these icy worlds and conducting experiments on their surfaces or in their subsurface oceans presents an exciting frontier. Future missions may aim to develop landing technologies capable of safely touching down on Europa's or Ganymede's surface, enabling scientists to directly sample materials and analyze their composition in ways that orbital observations cannot achieve. These in-situ missions could unlock the secrets of the moon's geology, ice dynamics, and potential biosignatures. Instruments designed to analyze ice samples, measure subsurface water chemistry, and even conduct biological assays could revolutionize our understanding of these moons. If microbial life were to be discovered, it would fundamentally change our perspective on where life can exist and what forms it might take. The exploration of Jupiter and its moons also raises questions about the future of human presence in space. As technology advances, the possibility of establishing outposts on these icy moons could become a reality. Such outposts could serve as bases for further exploration of the outer solar system or even as staging points for missions to more distant destinations, such as the outer planets or the Kuiper Belt. Establishing a human presence in the Jovian system would represent a significant leap in our capabilities and could yield profound insights into both planetary science and the potential for human adaptation to extraterrestrial environments. As we navigate these exciting possibilities, it is crucial to maintain a commitment to responsible exploration. This includes adhering to planetary protection protocols to avoid contaminating celestial bodies and preserving the scientific integrity of our investigations. Engaging with ethical considerations surrounding space exploration is essential as we push the boundaries of what is possible. The principles of stewardship, respect for other worlds, and the potential consequences of our actions should guide our exploration efforts as we venture into the unknown. In addition, the exploration of Jupiter prompts us to think about the long-term future of humanity. The knowledge we gain from studying gas giants and their moons will not only enhance our understanding of our solar system but also prepare us for the challenges of future exploration beyond our immediate neighborhood. As we confront global challenges such as climate change, resource depletion, and population growth, understanding planetary systems and their dynamics may provide valuable lessons about resilience, adaptability, and sustainability. The story of Jupiter is one of ongoing discovery, weaving together threads of science, technology, philosophy, and human curiosity. As we advance in our exploration efforts, we stand on the shoulders of giants, pioneers who have laid the groundwork for our current endeavors. Their contributions remind us that the pursuit of knowledge is a collective journey, driven by the aspirations of humanity to explore the unknown and understand our place in the cosmos. In summary, the exploration of Jupiter is not simply about studying a distant planet. It embodies the essence of human curiosity and the desire to unravel the mysteries of the universe. Each mission, each discovery, and each question answered fuels our collective quest for understanding and pushes the boundaries of what we know. As we continue to investigate Jupiter, its moons, and the broader implications of our findings, we embark on a journey that transcends scientific inquiry. It is a quest for connection, insight, and a deeper understanding of the universe and our role within it. In the coming decades, as missions to Jupiter unfold, we will undoubtedly encounter new challenges and breakthroughs that will reshape our understanding of the gas giant and its environment. Whether through the lens of a distant telescope or the instruments of a spacecraft navigating the harsh radiation of the Jovian system, our journey to understand Jupiter and its moons will continue to captivate our imaginations and inspire future generations to look to the stars and ask the age-old question, what else is out there? With each revelation, we inch closer to unraveling the secrets of the cosmos, opening new doors to exploration, and enhancing our appreciation for the wonders of the universe. The exploration of Jupiter and its moons also invites us to reconsider the nature of our own planet and its environment. As we study the atmospheric phenomena of Jupiter, including its iconic Great Red Spot, we gain insights into the dynamics of weather patterns on Earth. Understanding the mechanisms that drive storms, jet streams, and atmospheric circulation on Jupiter can provide valuable analogs for improving weather prediction models here on Earth. The intricate interactions between Jupiter's atmosphere and its immense gravitational field demonstrate how planetary systems can influence one another, emphasizing the interconnectedness of celestial bodies. Furthermore, studying Jupiter's magnetic field and radiation belts can shed light on space weather phenomena that affect not only other planets, but also our own technological infrastructure. The radiation environment around Jupiter is significantly harsher than that of Earth, and understanding how its magnetosphere interacts with solar wind and cosmic rays could enhance our ability to protect satellites, astronauts, and technological systems from space weather-related disruptions. Insights gained from Jupiter's magnetic field could guide future designs of spacecraft and satellites, allowing us to mitigate risks associated with operating in hostile environments. As we embark on this multifaceted exploration of Jupiter, it is crucial to foster a spirit of global collaboration. The challenges of exploring distant worlds are too great for any single nation or organization to tackle alone. International partnerships in space exploration not only leverage shared expertise and resources, but also inspire a sense of unity among nations, emphasizing our shared goals of discovery and understanding. Collaborative missions can pool scientific knowledge, engineering capabilities, and funding, enhancing the scientific return and fostering goodwill among participating countries. The lessons learned from the study of Jupiter also extend to broader discussions about planetary stewardship and the ethical implications of exploration. As we venture into the realms of other worlds, we must consider the responsibility that comes with our capabilities. The scientific community is increasingly aware of the potential consequences of contamination, both in terms of preserving extraterrestrial environments and ensuring that our findings remain scientifically valid. Establishing and adhering to planetary protection protocols is vital to maintaining the integrity of our research and the ecosystems we seek to study. Jupiter's moons, particularly Europa and Ganymede, represent some of the most intriguing targets for future exploration due to their potential to harbor life. These icy bodies possess subsurface oceans, which may contain the essential ingredients for life as we know it. As we explore these moons, we should remain mindful of our impact, ensuring that we do not disrupt any potential ecosystems. The search for life elsewhere in the universe raises profound questions about the nature of life, consciousness, and the possibility of alternative forms of existence. In parallel to our scientific endeavors, the exploration of Jupiter and its moons has a profound cultural significance. The mysteries of the universe have long been a source of inspiration for art, literature, and philosophy. The stories we tell about celestial bodies shape our collective imagination and our understanding of our place in the cosmos. The exploration of Jupiter serves as a reminder that the pursuit of knowledge is not merely a scientific enterprise. It is an integral part of what it means to be human. Our curiosity drives us to seek answers to fundamental questions. What lies beyond our world? Are we alone in the universe? How did we come to be? As we stand on the brink of a new era of exploration, the excitement surrounding upcoming missions is palpable. Each launch represents a leap into the unknown, a commitment to uncover the secrets of the cosmos. The data collected from these missions will likely yield new theories, challenge existing paradigms, and deepen our understanding of planetary systems. The anticipation of discovering new phenomena or even signs of life on other worlds fuels our collective curiosity and sense of wonder. As we look forward to the discoveries yet to come, we can reflect on the profound impact that previous missions have had on our understanding of Jupiter and its moons. The Galileo mission, for instance, provided a wealth of information about Jupiter's atmosphere, magnetic field, and its diverse moons, reshaping our understanding of gas giants and their environments. The data from the Juno mission continues to enhance our knowledge of Jupiter's internal structure, atmospheric dynamics, and magnetic field. These foundational missions have set the stage for the next wave of exploration and laid the groundwork for future generations of scientists. In addition to the scientific community, the exploration of Jupiter engages the public imagination and fosters interest in space exploration. The visual imagery captured by spacecraft, such as the stunning images of Jupiter's swirling clouds and intricate storms, captivate audiences around the world. Educational programs, outreach initiatives, and media coverage play a crucial role in inspiring the next generation of scientists, engineers, and explorers. The stories we tell about our explorations resonate with people of all ages, igniting a passion for discovery and an appreciation for the wonders of the universe. As we continue our journey into the depths of the cosmos, we should also reflect on the broader implications of our explorations. The study of gas giants like Jupiter informs our understanding of planetary formation and evolution, providing insights into the conditions that lead to the development of habitable worlds. By examining the processes that govern the formation of gas giants, we can enhance our knowledge of how solar systems evolve and the factors that influence planetary habitability. Furthermore, as we confront global challenges on Earth, such as climate change and resource scarcity, the knowledge gained from studying planetary systems can inform our approach to sustainability and environmental stewardship. The dynamics of Jupiter's atmosphere and the interplay of various factors that influence its climate can provide valuable lessons for understanding Earth's climate system. The exploration of other worlds challenges us to think critically about our own planet and the steps we can take to ensure its long-term health and resilience. In conclusion, the exploration of Jupiter and its moons is a multifaceted endeavor that transcends the boundaries of science, technology, culture, and ethics. Each mission and discovery contributes to our understanding of the universe and our place within it. As we navigate the complexities of space exploration, we must approach our endeavors with curiosity, responsibility, and a commitment to fostering a sustainable future. The journey to unravel the mysteries of Jupiter is just beginning, and as we embark on this path, we carry with us the hopes and dreams of generations past, present, and future, a testament to humanity's unyielding quest for knowledge and understanding. Through our explorations, we continue to write the story of our existence in the cosmos, reminding ourselves that the universe is vast, full of wonders yet to be discovered, and waiting for us to explore its depths. The exploration of Jupiter not only captures the essence of human curiosity but also serves as a critical framework for understanding broader scientific concepts that can have profound implications for life on Earth and beyond. As we venture further into the mysteries of this gas giant and its intriguing moons, we must acknowledge the interconnected nature of our scientific inquiries and the way they shape our understanding of the universe. One of the most compelling aspects of Jupiter's study is its role as a prototype for gas giants across the universe. By examining Jupiter's atmospheric dynamics, scientists can draw parallels to the gas giants found in exoplanetary systems. The characteristics of Jupiter, such as its cloud formation, storm activity, and atmospheric circulation, provide a template for understanding how these processes might occur on distant planets orbiting other stars. As we develop techniques for observing exoplanets, the data gathered from Jupiter will inform our models and enhance our ability to interpret observations from afar. Moreover, the existence of exoplanets that share similar characteristics to Jupiter, such as those classified as hot Jupiters, challenges our traditional notions of planetary formation and migration. These large gas giants, which orbit very close to their host stars, raise intriguing questions about the processes that govern planet formation and the potential for atmospheric retention. By comparing the atmospheres and compositions of these exoplanets with those of Jupiter, scientists can gain insights into how different environments influence planetary evolution and stability. As we deepen our understanding of Jupiter's atmosphere, we are also confronted with the complexities of weather systems on a planetary scale. The intricate cloud bands, cyclones, and anticyclones that define Jupiter's atmosphere showcase the dynamic nature of gaseous worlds. Researchers are particularly interested in understanding the mechanisms that drive the formation and maintenance of features like the Great Red Spot, a massive storm that has persisted for centuries. Investigating the energy sources and interactions that sustain such phenomena could reveal underlying principles applicable to both planetary atmospheres and climate systems on Earth. The implications of this research extend beyond our immediate solar system. By studying the weather patterns and atmospheric dynamics of gas giants, we can better understand the potential for similar processes on exoplanets. The quest to identify habitable zones around stars has been a significant focus in the search for extraterrestrial life, and understanding the atmospheric conditions that support habitability is essential. If we can draw connections between Jupiter's atmospheric processes and those observed on exoplanets, we could refine our criteria for identifying potentially habitable worlds. In the context of astrobiology, Jupiter's moons offer tantalizing possibilities for the existence of life. The subsurface oceans of Europa, Ganymede, and Callisto are particularly compelling targets for exploration. These moons, with their icy crusts and hidden oceans, may harbor the necessary conditions for life to exist. The upcoming missions, such as the Europa Clipper and JUICE, will focus on characterizing these environments, searching for signs of habitability, and assessing the potential for life. The discovery of even the simplest forms of life on these moons would revolutionize our understanding of biology and the conditions that support life. In addition to astrobiological inquiries, the exploration of Jupiter's moons may also shed light on the geological processes that shape celestial bodies. The interplay between tidal forces exerted by Jupiter and the icy shells of its moons could result in geological activity, creating a dynamic environment that is of great interest to scientists. Understanding how these forces influence surface features, such as ridges, fractures, and possible plumes of water vapor, can provide insights into the geological history and evolution of these moons. As we consider the potential for life on Jupiter's moons, it is essential to think about the ethical dimensions of our explorations. The search for extraterrestrial life raises questions about how we should approach the study of potentially habitable environments. The principle of planetary protection mandates that we take measures to prevent contamination of these moons with Earth-based organisms. As our exploration capabilities advance, so too must our commitment to ethical exploration, ensuring that we do not disrupt any potential ecosystems. Engaging with the public and fostering a sense of stewardship towards celestial bodies is critical as we continue our explorations. The excitement surrounding the search for life in the universe can inspire a sense of wonder and curiosity among people of all ages. Educational initiatives that highlight the importance of space exploration can engage future generations and promote a culture of scientific inquiry. Public outreach efforts should emphasize not only the scientific discoveries but also the ethical considerations of exploring other worlds, fostering a sense of responsibility and respect for the environments we study. Moreover, the story of Jupiter and its moons is not only a narrative of scientific exploration but also one of international collaboration. The partnerships formed between space agencies, research institutions, and private companies underscore the importance of shared goals in advancing our understanding of the cosmos. As we embark on complex missions, pooling resources and expertise will be essential to overcoming the challenges of exploring distant worlds. The global nature of space exploration emphasizes our shared human experience and the pursuit of knowledge that transcends national boundaries. As we look to the future, the potential for human exploration of the Jovian system raises fascinating possibilities. While robotic missions are invaluable for gathering data and conducting preliminary investigations, the prospect of sending humans to explore these distant worlds opens a new chapter in our understanding of the universe. Human missions could provide a level of adaptability and creativity that robotic missions may lack, allowing for more nuanced exploration and direct engagement with the environments we study. However, such missions would come with significant challenges, including the harsh radiation environment of Jupiter and its moons. Developing technologies to protect astronauts from these hazards will be a critical area of research. Innovations in spacecraft design, radiation shielding, and life support systems will be essential for ensuring the safety and success of any potential human missions to the Jovian system. In contemplating the future of exploration, we must also acknowledge the broader implications of our discoveries for humanity as a whole. The search for extraterrestrial life and our exploration of gas giants like Jupiter challenge us to rethink our place in the universe. As we gather data and make discoveries, we confront fundamental questions about our existence and the potential for life beyond Earth. The realization that we may not be alone in the universe has the power to transform our understanding of life, consciousness, and our responsibilities to one another and to the cosmos. As we conclude this discussion of Jupiter and its moons, it is clear that our journey of discovery is far from over. Each mission, each finding, and each new question enriches our understanding of the universe and our place within it. The mysteries of Jupiter continue to captivate our imaginations, fueling our drive to explore the unknown. Looking ahead, we stand at the threshold of new discoveries that will undoubtedly reshape our understanding of gas giants and the conditions for life in the universe. The exploration of Jupiter is not merely a scientific endeavor, it is a testament to the enduring spirit of human curiosity and our relentless pursuit of knowledge. As we continue our journey into the cosmos, we carry with us the aspirations of generations past, present, and future, an unbroken thread of exploration that connects us to the stars. Ultimately, the story of Jupiter is a story of interconnectedness, between worlds, between scientific disciplines, and between humanity itself. As we explore the vastness of the cosmos, we deepen our understanding of our own planet, our place in the universe, and the potential for life beyond Earth. The exploration of Jupiter serves as a reminder that the quest for knowledge is a collective journey, one that requires collaboration, innovation, and a commitment to stewardship as we navigate the complexities of space exploration. As we embark on this exciting path forward, we do so with a profound sense of wonder, anticipation, and responsibility. The discoveries yet to be made in the Jovian system promise to enrich our understanding of the universe and ignite our imagination, inspiring future generations to reach for the stars and continue the age-old quest for knowledge. In the end, the exploration of Jupiter is not just about uncovering the secrets of a distant planet, it is about forging connections between ourselves, our planet, and the vast cosmos that surrounds us. Through our explorations, we contribute to the narrative of humanity's journey through the universe, a journey filled with wonder, discovery, and the relentless pursuit of understanding. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.